Could you bond oxygen? Destiny, right? So when you look at all these hydrogens, like if you draw this out, you got 3 carbons, right? And you just got hydrogens all over these. So it looks like this, all right? Now, the only way an oxygen, like let's say a water does come along like this, and this oxygen is looking, what is it looking for? It's looking for a positively polarized hydrogen. That's the only way you're going to get a hydrogen bond. It's not just going to bond with any old hydrogen. So are any of these hydrogens positively polarized? Let's look at our key. A donor, meaning a positively polarized hydrogen, is one that is bonded to. So I will say this molecule too is going to have quite a few. And don't feel like you have to draw every single one of those out. Just show me at least one example. Okay. Kendall. The one I circled? The one above it.
Obviously, you're gonna have to bind the nitrogen to carbon.
Yep.
And then you're gonna have to do
Well, you've got a CH3 group, right? That is branched off this nitrogen, and how many are branched off that nitrogen? 3 groups of CH3 branched off that nitrogen. So you won't have any lone hydrogens bonded directly to the nitrogen. So try it that way. Okay, any other questions on this one? Okay. Ouch. Okay. So would y'all like to work some more of these chapter 8 problems, since that's kind of still newish, before we go back to chapter 7? Okay, I'm seeing some nods. So this is literally where we left off from class. All right, this problem says, so these are your chapter 8 slides if you're looking for all that. It says a gas has a volume of, the moment you read a problem that's like a gas, blah, 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 you know you need either the combined gas law or the ideal gas law, okay? If it's talking about a gas, that's what you need. Unless it specifically has like delta H or delta S in it, okay? But it says the gas has a volume of 350 milliliters at 45 degrees Celsius. If the volume changes to 400 milliliters, what is the new temperature? So again, you read this and you're like, all right, where do I start? I know it's like a problem about a gas, but that's all I know. And it says report the new temperature in degrees Celsius. So what should you do? First, if you don't know what to do, just start with the combined gas law. You don't read anything about moles of gas here, right? Like it's not asking for how many moles of gas. It's not telling you you have 3 moles of gas or something like that. Nothing about moles of gas, right? If it says something about moles of gas, you need the ideal gas law. But if it doesn't, nothing about moles of gas here. Here you're just volume and temperature and volume. Then you need to start with the combined gas law, which is the P1 V1 over T1 equals P2 V2 over T2. Okay. Now, where do we go from here? And in the problem, I would tell you at constant pressure. Okay, so now that you read that, what should we do? Take pressure out. So our equation that we're working with is V1 over T1 equals V2 over T2. Pressure is not changing. Sorry. It's okay. Now, if you want to, at this point, you can go through and label the variables in your problem. You can write them out on the side. Sometimes I'll see students say V1 equals 350 milliliters, okay? You know, we're looking, oh, we have V2 equals 400. Now, I'll see students do this, or I like to just say, all right, this is V2, this is V1, because, you know, on an exam, you're trying to save as much time as possible. And this is my T1, that first 45 degrees Celsius. Okay. Now, I actually don't know that I've said this in class. Hopefully I did. I can't remember if I did. All of these need to be worked in Kelvin. Okay. Have we ever actually had a math equation that we worked in Celsius, unless it was a temperature conversion where you're specifically solving for Celsius or something? Everything we've ever done is always in Kelvin, and it's no different here. So if you're given a Celsius temperature, always convert it to Kelvin first. So I'm going to take this 45 degrees Celsius and do what to it? So you got to have this number memorized for the exam. And that should be 303, 313. Is it 318? So the temperature I will plug in is 318.15 Kelvin. All right, and we're solving for, it says, I'm going to highlight my question here. What is the new temperature? So I'm solving for what variable? T2. So we have yet to work a problem like this where what we're solving for is in the denominator. That's interesting. There's a couple ways you can do this. There's a long and a short way. And I guarantee all of y'all are going to say, show me the short way. Take the reciprocal of the whole equation. Get that out of the bottom. Do not leave T2 in the bottom. The quickest way to get it out of the bottom is to flip the whole thing. Now, hear me out. So the reason why I drew an arrow on this side and this side is because you can't just flip one side. You flip one side, you got to flip both sides of the equal sign. So when you do that, you have T1 over V1 equals T2 over V2. A classic mistake is students will flip one half. They'll forget to flip the other side. Now you cross multiply both sides by V2. And what do you have? You have T2 by itself in the numerator. Okay. So my equation is V2 canceled on the right side. So I marked it out. When I flip both sides and then I moved V2 around, my equation is that I'm running out of room. Move this up. Is that oops. Oh, shoot. V2 times T1 divided by V1 equals T2. That's my equation. I just plug everything in. This sound, I remember last semester during finals week, we would never hear the sound. And then literally when students show up to take the final, this went on the whole time. I wanted to shout. Let's do it again. So here's our equation when we take P out, and what we're solving for is T2. So what we did is we flipped the whole equation. We took the reciprocal of both sides. T2 over V1 equals, what did I wrote the wrong thing, didn't I? T1 over V1 equals T2 over V2. All right. Now, to get T2 by itself, what we did is we cross multiply both sides by V2. Okay, and then it canceled here and here. So what we're left with when you clean that up is V2 times C times T1 over V1. This is the equation I'm using to solve this problem. Now you just plug everything in. So in the space that I have left, V2 is 400 milliliters, so we'll do 400 milliliters times T1 is 318.15 Kelvin. Divide that by V1, which was the 350 milliliters. 363? 363.6 units are Kelvin. So volume went up, which means temperature had to go up, because remember, temperature and volume are proportional, like the hot air balloon thing. You increase the temperature of the gas, the volume is going to increase at constant pressure. I think the hardest part here is getting to the right equation. The easy part is plugging everything in. $363.6 Kelvin. Okay. That's that one. Let's do another one. Gas hairspray can. That's embarrassing to say, probably. What happens when you have two kids? All right. Temperature of 27 degrees Celsius and a pressure of 30 psi. If the gases in the can reach a pressure of 90 psi, the can will explode. To what temperature must the gases be raised in order for the can to explode? Assume constant volume. Right? So what equation do we need? Do what? P over T? Just this? What's the full thing we need? So yeah, your options are you need the combined gas law or the ideal gas law. Combined, why do you know you need the combined gas law? Because it doesn't say anything about moles. Okay, so we need P1 V1 over T1 equals P2 V2 over T2. Now, do we need to, is anything being held constant? Huh? Constant volume, which is why Kendall was saying P over T. He was already 2 steps ahead. Okay, so we're gonna take volume out, and it's gonna be the P1 over T1 equals P2 over T2. Okay. So that's what we're gonna use now. We're given a temperature of 27 degrees Celsius. 300.15. So when you convert that to Kelvin, that's going to be your, this is T1, the first temperature given. And then you have 30 PSI is P1, 90 PSI is P2. Okay. So, says to what temperature must the gases be raised? Again, we're solving for temperature here. So y'all know this is how to do this now because we're solving for T2. So y'all tell me what to do. Take the reciprocal, T1 over P1 equals T2 over P2. And do what? Get rid of P2. Well, we're not getting rid of it. We're just moving it to the other side. Cancel, cancel. Everything in. So it's going to be P2, which is the 90 PSI. Fortunately, both of these units for pressure, look at them. They're the same, PSI and PSI, so we don't have to convert anything. times the 300.15 Kelvin divided by P1, which is the 30 PSI. And what's our answer? I think there are people in this world that actually would throw a hairspray can into a fire to watch it explode. I get so mad. We have a fire pit in our backyard. I told you my husband is like a woodworker. So he'll have like old cans of, I don't know, stuff that shouldn't be in a fire. And I'll walk out to a fire pit and I'll just see these smoldering cans and I'll be like, what is this? You're gonna get cancer. Stop.
Yeah, that's not a funny answer for.
900 point what? Oh, 4.5. Sorry. I probably just misheard that. All right. Look at this one. This is another very similar problem to what we've been doing. Let me see if I can find something different.
If you have anything that goes over like,
Millimeter mercury.
mercury and like PSIs and Pascal and stuff like.
Uh-huh. Yeah, I know I have a, trying to look at this one, gases one. None of these problems practice with the ideal gas law. So, which we've just been using the combined gas law and getting rid of the thing that's held constant. That's what we've been doing so far. This one, if you read it, so we'll do that in just a second, Keely.
That's fine.
A gas has a volume of 2.84 liters at 1 atm, 0 degrees Celsius. At what temperature does it have a volume of 7.5 liters, 520 milliliters mercury? This one is actually a little step harder, I think, because nothing's being held constant. And look at, if we go through and label, so we're gonna need the full combined gas law here, which we've yet to do one of these. Use the full thing. It's the same what you've been doing, is you just have a few more variables to keep up with, okay? All right, so what I like to do again is I just go through a volume. So this is V1. Here's a pressure, this is P1. Here's a temperature, this is T1. And this is at what temperature, so we're solving for T2. And volume here, so this is V2. Pressure here, P2. You gotta be able to recognize these units to quickly label that. So we're gonna use the full gas law and we're solving for T2, which is on the bottom again, so y'all know, flip both sides. But it is more complicated as well because look at your units for pressure. One's in ATM, one's in millimeters of mercury. It doesn't matter which way you go, but they both need to be the same. Okay, now on the ideal gas law, it does matter what your unit of pressure is. It can't be in anything except for ATM. You always work the ideal gas law with units of ATM on your pressure. Here though, doesn't matter if you pick P1 and convert it to millimeters mercury or pick P2 and convert it back to ATM. 760. So if we do that, Kendall just said 1 ATM, which is P1. This is our P1. We're just gonna say for every 1 ATM, it's 760, and this is really easy math, right? So our P1 is, instead of 1 ATM, we can say that equals 760 millimeters mercury. Now we have both in units of millimeters mercury, P1 and P2, and we can plug both of those in, okay? So to just give you one practice one with the full combined gas law, we'll work this one and then we'll move on to something else because I think we've done several of these now. Since T2, that's exactly right, Destiny. Since T2 is in the denominator, we need to flip the whole thing. So it will become T1 over P1 V1 equals T2 2 over P2 V2. And now I have to move what? I gotta move P2 and V2. I want T2 by itself, so I'm just gonna move them both at the same time. We'll say times P2 V2 times P2 V2. And that cancels on this side, both of them. So my new equation is P2 times V2 times T1 divided by P1 V1. These are multiplied. So again, this isn't calculus. This isn't even crazy hard algebra. It's just that there's 6 variables you have to keep up with. All right, and then the last thing, what's the last thing we have to do before we just plug everything in? Temperature's got to go to Kelvin. So if it's 0 degrees Celsius, that's easy. It's 273.15 Kelvin. That will be T1. So P2, we'll start plugging all this in. It's 520 millimeters mercury. V2 is 7.5 liters. T1 is 273.15 Kelvin. P1 we converted to 700. It was 1 ATM, but we have to have the units match the other variable of pressure. So it's 760 milliliters mercury. And V1 is up in the problem, 2.84 liters. And all of this equals T2, which is what we're solving for. And make sure unit-wise millimeters mercury cancel, liters cancel, and you're left with just Kelvin.
Oh, no, I'm an idiot. Wait, no, I'm not.
No, you're
I'm
not.
lost.
I will say, when you have, look, you have a multiplication sign on the bottom. See that? So if you plug all this in your calculator at one time, which you don't have to, but if you do, you better put that bottom part in parentheses. If not, it will only divide by 760 and it won't actually also divide by 2.84. Okay, so to be safe, put that in parentheses if you do it all at once. But you don't have to do it all at once. You can multiply out the top, you can multiply out the bottom separately and then divide those numbers. Did you get found?
I think so. We'll see when the answer comes.
Oh yeah, anybody got the answer? $980 point Kelvin. Is that what y'all got? Anybody else verify? That's what you got? Is that what you got, Cooper? Macy, did you get it? So for sure, it's probably around 3,900. Anybody double checking?
So why did you
Yeah, what's up?
put everything on top? Like, I thought you were supposed to flip it because
Flip what?
we were trying to find T2. So we were supposed to flip both sides.
Yeah, we did.
We did. And then, well, how did?
Did I get them wrong? You didn't get what? What'd you get? 493? 493.5? Well, I did not bring a calculator today. Oh. Okay, so we're gonna do. Okay, I got 494.19. So Destiny, try it again. Maybe something. Did you get it? You still get the 3,000? Let me see your calculator. You're doing it all at once, right? Okay, but when you do it all at once, so every time you're only putting the 2.84 in parentheses. So what's happening is it's dividing by the 760. It's not actually also dividing by 2.84. So when I mean put it in parentheses, you got to see how I have both of mine in parentheses. Start the parentheses in front of the 760. And then say times the 2.5. So you're multiplying the two numbers in the denominator, but in the whole problem, you're not also dividing by the 2.84. So actually just take your answer, 3,980.8, and divide it by 2.84 and tell me what you get. Well, that's not gonna be right. So anyways, it should be 493. That's what we said?
Okay.
Got it? Okay.
I was also putting in 720, not 760.
There you go. That'll mess it up. Okay, so that's plenty of practice, I think, with the combined gas law. I want to jump over to these chapter 7 review slides. Keely, you said you wanted to look at conversions between units.
Yeah, but it's okay. We can get to it.
No, real quick, we can do this. So like, let's say that I give you, 0.5 ATM. Okay. And you have another pressure that's like, 40.2 PSI. If you have two units like this in a gas law problem, you have to convert one to the other. They have to match. The units have to match for pressure or for volume or for whatever. So you pick one, you convert to the other. This is where you need to know what those unit conversions are, okay? It's just a matter of memorizing those. That one ATM is equal to 14.7 PSI. Okay, you can directly convert from one to the other. Okay, so it doesn't matter which one you pick. If you pick this one, you just need to multiply it so that ATMs cancel. For every one ATM, it's 14.7 PSI. Okay.
I think it's just probably remembering all the numbers.
So canceling the ATMs. So you do 0.5 times the 14.7, which should be 7.35 PSI. Okay, and then you'd have it converted and be ready to go. All right. So if you're working with the combined gas law, it does not matter which unit, ATM, PSI, millimeters mercury, as long as both variables of pressure have the same unit. If you're working in the ideal gas law, because your gas law constant R has units of ATM in it, your pressure term has to be in units of ATM. So it depends which law you're using. That's a safe thing to think. Always work it with ATM. Yeah. Did that help, Keely?
Yeah, it did. Thank you.
Okay. I'm happy to do more.
I think it's probably just like having to remember all
Those numbers, yeah. Okay. Before we go, if y'all remind me, I'm watching the time. We got like 20 minutes left. We can make a quick list of things that y'all need to have memorized. Okay. All right. As we exercise, our bodies metabolize glucose with oxygen, converting it to CO2 and water to supply the energy necessary for physical activity. Write a balanced equation. So this is chapter 7 stuff. Write a balanced equation for the metabolism of glucose, okay? So it says you've got glucose and it's gonna react with oxygen, which is O2. So to write this out, you would say C6H12O6 plus O2 is going to give you CO2 plus H2O, and then you got to balance it. So I'm going to try a 6 right here in front of CO2, and a 6 right here in front of water. And then that gives me 12 and 6 was 18 oxygens. And I already have 6, so I need to come back and put another 6 in front of oxygen. So that would be our balanced reaction when done. Okay, so that should be the easy part for you guys. Number 2 says each mole of glucose produces 678 kcals of energy. What is the sign of delta H for this equation? What's the key word here? That's right, Keely. The key word is produces. If you're producing heat, producing energy, you're giving off heat, giving off energy. Energy is a product. Keyword produces meaning we can say plus heat. Is this exothermic or endothermic? Makes it exothermic, and we know exothermic is negative delta H. So what that means is for every 1 mole of the C6H12O6, we are producing negative 678 kcal per mole of energy. Okay, but that's not what the question asks you. The question just asks you sign of delta H. It's negative. Okay, let's go to question number 3 below. An individual jogging at 5 miles per hour. That sounds slow, but when you're jogging, that's probably not that slow. For 30 minutes would burn 272 kilocalories. How many moles of glucose would be needed, would need to be metabolized to generate this amount of energy in the body? So we supply our body with energy, and when we do physical activity, our body's using that energy rapidly, depending on what kind of exercise we're doing. So how much energy would we need to supply our body with to produce the amount of energy needed to run here? So you're given these numbers, the 5 miles per hour and the 30 minutes. That's some added info here. We don't need to plug those numbers in for anything. It says we're going to burn 272 kcal of energy. So if our body had no glucose in it, you would be dead. But hypothetically, if we had no glucose, but we needed to do this, how much glucose would we need to consume so that our body could burn this amount of energy? Do you have a relationship between glucose and kcals? That's why I just wrote this out. And what problem 2 tells you, each mole of glucose produces 678. So you can actually just relate these 2 numbers, the absolute value of them. When it's asking you the sign of delta H, the negative for sure matters. But here when you're doing these conversion problems, you just need the absolute value of those numbers, okay? 1 mole of glucose, if I burn 1 mole of glucose in my body, it's gonna produce 678 kcal of energy. So if we're gonna burn 272 kcal, we know for every 678 kcal of energy, 1 mole. I'm just gonna put a capital G for glucose. That's the C6H12O6. I can cancel out units of kcal and convert to moles of glucose. Kindle. That's what I was talking about. Up here, if we're talking about our delta H, yes, it's a negative 678. But when you're doing conversion problems like this, you just want the absolute value of it, okay? Because we have to consume that amount, or that amount of energy has to be consumed, is going to be produced by 1 mole of glucose. It doesn't make sense from the perspective of the body to say, if I consume 1 mole of glucose, I'm making negative energy. No, it's going to produce that amount of energy. Now, because it's being produced from the viewpoint of the equation, it's a, anyways, just the absolute value here. Okay. That's all you have to do on this one. 272 divided by 678. What is it? All right. And my nutrition people, an energy bar contains 20 grams of glucose. I used to say like a Cliff Bar or something. I really don't like Cliff Bars. I don't think they're that great. Do what? I haven't had a chocolate chip in a long time, to be fair, but I'm not big fans of them. I'll eat Lar bars. But recently, I've not been into Lar bars. I used to eat them, like the coconut ones, I think are good, but I haven't had them in a long time because I've got burnt out on them. All right, an energy bar. You pick your brand. Contains 20 grams of glucose. How many energy bars? This is also why I don't eat a lot of energy bars, because they have so much glucose. How many energy bars would need to be consumed to generate the same amount of energy in question 3? So read what the problem's telling you. An energy bar, 1, contains 20 grams of glucose. So write that out. 1 bar is going to be related to 20 grams G, and I'm going to put a capital G for glucose. 20 lowercase g grams of glucose. So 0.4 moles of glucose, 0.4 moles of glucose, that's the amount of mole, that's the number from problem 3. That many moles of glucose is going to allow us to produce 272 kcal of energy in the body, right? 272 kcal, if we burn 0.4 moles of glucose, we'll get that amount of energy out of it. That's what we calculated in number 3. So I'm going to take this 0.4 moles and say, okay, if I need to consume 0.4 moles of glucose, I got some energy bars. How many energy bars do I need to eat to get this many moles of glucose in my body so that I can then go exercise and produce the amount of energy I need to exercise? What do we need to do here? We need to convert, or yeah, we got moles of glucose here. We need to convert that to grams, and then we can use this relationship to go from grams to energy bars. So for every 1 mole of capital G glucose, how many grams is it? We need a molar mass, don't we? We're not going to take the time to calculate that, but what you would do is you would look up, we got C6H12O6. You'd say, okay, carbon, 6 times, the 12.011. Hydrogen, 12 times the 1.01. Oxygen, 6 times 16. You add all that up and you're going to get 180. I think it's like 0.16 or something grams, okay? That's the molar mass of glucose. And you could totally calculate that if you had to. And then we know that if we consume 20 grams of glucose, that comes from 1 bar. That's 1 bar. So I'm taking the amount of glucose from problem 3 that I calculated that's associated to that 272 kcals. And I'm canceling moles of glucose, canceling grams, using the molar mass. So how many bars would I need to eat? .6 energy bars. Whoa.
They have a lot of carbs in it too.
Fortunately, your body has a reservoir of glucose in it.
My boyfriend ate so many energy bars 1 year, and he got kidney stones.
I wonder how that works.
Something about like, so like guys, kidneys can't process certain things in them.
My father-in-law's had like 100 kidney stones. You got kidney stones? Okay, good. All right, 3.6. All right, does that problem, anybody have questions on that problem? I think that was a very challenging problem. You had like that one on an exam, that would be quite a few points there. Okay. Any questions on that? Another one like that? I'll just have to see if I can come up, I don't actually have one on these slides. But maybe I can come up with something for Monday reviews. So I'm gonna be here for those. Okay, let's do one more problem and then we'll make a list of stuff to memorize, okay? So this problem, believe it or not, actually, Destiny, is very much like the one we just did without all the energy bar stuff. But what it is it's giving you a chemical reaction, okay? We wrote one out for the metabolism of glucose. And it's giving you the delta H. And then it's asking you to convert how much heat in kcal would be absorbed with 0.77 moles of CH4. This is like in the problem up here where I said, if you're gonna burn 272 kcal, how many moles of glucose? It was just a conversion between kcals and moles. Same idea here, but you're starting with moles and you're going to kcals. You have to look at this reaction and derive that relationship, which is very easy. You just look at the coefficient, which is a 1 for CH4. Say if I consume or if I react 1 mole of CH4, I'm producing 213 kcals. So again, you take the absolute value and you say for every 1 mole of the CH4, that is equivalent or related to 213 kcal. It does not matter if you write the kcals on top or bottom right now. Okay, but this relationship is what you need to answer this problem. Okay, you are in the problem, it gives you 0.77 moles of CH4. You're going to start with that number. Then you're going to use this relationship we just wrote out to cancel moles and convert to kcal. Okay. I'll say that again. You're going to start with the 0.77 moles of CH4. And you're going to use this relationship in the box that we just wrote out to cancel moles and convert to kcal. 0.77 moles CH4. Yeah, and then you're just going to put for every 1 mole CH4, it's 213. This is where, again, using the absolute value of kcal. Moles cancel, moles of CH4, give you 0.77 times 213. That's a hard question for me to answer because it just depends on how the question's written, really. If I said you've got, like, look at this next one, you've got grams of oxygen. Well, knowing that you can look at any chemical reaction, if I give you the delta H, and you can come up with a moles to kcal relationship for any reactant or any product. Okay, I could say 2 moles of oxygen, 213 kcal. 1 mole of CO2, 213 kcal. Okay, all of these, just looking at the coefficients, are related to your delta H. And that is your conversion between moles and kcals. You, from previous chapters and earlier in this course, have learned how to go from grams to moles. That's molar mass stuff, okay? So this one would not be a one-step problem. It just depends on how the problem's written and what information is given. All right. So anyways, you do this one, say 0.77 times 213. I don't know what the answer is, but. All right. How do you guys feel about delta S and delta H? Okay, we'll do this one, and then that's probably be close to time. We'll make a list of stuff to memorize. So this will be the last one we'll do. I'll pick up with these on Monday. You can come to those reviews. For those of you who are going to get married in your future, don't plan your wedding at 3:30 in the afternoon. That's what I have to go to tomorrow.
On a Friday.
On a Friday.
Wow. They
All right.
don't think about anybody but themselves.
That's right.
Okay, we'll go on chart.
She's trailing off with her question. Am I gonna give you that table of delta S and delta H? In the past, I have not. But I'm gonna carefully consider. I know I'm gonna give you electronegativity chart. Wait, what? What was that, Kendall?
Say the future of that. You also said you're gonna give us, what charts in there?
I said, if you needed the heat of vaporization or heat of fusion, I would give you that chart. Do not try to memorize any of those numbers. I'm thinking, Kendall. I'm considering you guys. All right, let's do this one. Predict the sign of delta S, positive or negative. So again, remember, you're looking at these states of matter, solid, gas, liquid, solid, whatever it is. And you're looking at that, and you're looking at number of moles of stuff. Okay, you're saying, all right, do I got 2 reactants, 1 product? Do I got 1 reactant, 2 products? You're looking at, are things becoming more organized, more ordered, or more disordered? Okay, so here's what I noticed. I've got 3 moles of stuff, 2 here plus 1 more here from oxygen. I'm just looking at the coefficients and adding those up. And then I have a solid and a gas making a solid. I got 2 moles of stuff over here. Do what? We have not said what delta S is yet. You think it's negative? That's right. Remember, delta S is a measure of disorder. So if you are becoming more ordered, disorder is decreasing. And that is the hard thing about delta S. Okay, it feels backwards, but negative delta S for that one. Okay, because a solid is way more ordered than a gas. And you have a gas on your reactant side, but you don't on your product side. You have 2 things, 2 reactants, and only 1 product. So you're becoming more organized, more ordered. So that's a negative delta S. All right, glucose, that's a solid making this alcohol liquid and a gas. What do y'all think about this one? Positive or negative delta S? Positive delta S, because liquids and gases are way more disordered. Solids are more organized. So you'd say the reactant side is more ordered, the product side is more disordered. And as you go from reactants to products, disorder is increasing. Positive delta S. Okay, this one, I've got a gas and a gas. And on the other side, I've got a liquid and something aqueous. Gases are always more disordered. So here, it seems like you're going through something that's, did I say that right? Gases are always more disordered. That's what I said, right? You got something that's disordered, and then you're making something that's more ordered on the product side. So you're becoming more ordered. So disorder, is it increasing or decreasing? Decreasing, that's a negative delta S. Questions on that? I kind of walk through those fast. Disorder is decreasing, delta S is going to be negative. Yeah. Sorry, say that again. If you're thinking in terms of disorder. If you're thinking in terms of like, am I becoming more ordered? It's always the opposite, but think in terms of disorder. If disorder is increasing, positive delta S. If disorder is decreasing, negative delta S. So like here, I've got 2 plus 1, 3 moles of stuff. Here, I've got 2 moles of stuff. So here you would say, oh, 3 moles of 2 moles seems like it's more becoming more ordered, but you also have to consider the state of matter, okay? Which is really important there. And that's why we drew out these pictures. The gases look like this. The molecules are way far apart and they're zooming around like crazy, okay? But solids are nice and neat in a row here, and they look like that, so they're way more ordered. Okay. So last thing I'll do, you can head out if you need to, but I'm just gonna find some space. I got some space right here. Things that you need to memorize. So like for delta H, You need to know words like exo and endothermic. And you need to know what if the delta H is negative or positive. For delta S, you need to know how to tell if delta S is increasing or decreasing, okay, which is what we just kind of practiced. So how do you determine if you get a negative delta S or positive delta S, right? Now, this is not an equation. These are just kind of things I'm thinking about with these different topics, which were big topics in chapter 7. Okay, delta G, we do have an equation. You need to know that delta G equals delta H minus T delta S. And you got to remember that the temperature always has to be in Kelvin. The units on delta S always have to be converted to match the units on delta H. Okay, we practiced that a few times, I know, together in lecture. Temperature is always in Kelvin. All right, then we talked about equilibrium. We talked about reaction rates. There's really no equations to memorize there, but you need to know how to draw out reaction diagrams. Okay, labeling the delta G, labeling the activation energy. And then we talked about the equation in equilibrium for K and how K is equal to the concentration of products, all raised to the power of their coefficients, divided by the concentration of the reactants, all raised to the power of their coefficients. And then what K means. If you get a really, really large K, like K is a lot bigger than 1, what does that mean? If K is a lot smaller than 1, what does that mean? Is the forward or the reverse reaction favored? Remember that color-coded arrow? The blue and the red, or yeah, go look at that figure. That is what I'm talking about right here. And remember, you exclude things that are solid or things that are liquid. You only include things that are aqueous or gases in that equation. That was a keynote there. And then Le Chatelier's principle is the next big thing. I think these are all the big hitters in chapter 7, which we have not yet practiced a Le Chatelier's principle problem, but I've got a few that we will practice on Monday if you're able to come to those reviews. 10 a.m. and 1 p.m. And then the other two things from chapter 8, pressure conversions. For now, you need to know those. And then the combined gas law and the ideal gas law. Okay.